Hello everyone, I'm Norman Wahlberger. This is one of a series of videos on the sociology of pure mathematics, where I'm trying to encourage social scientists and other interested people in looking at pure mathematics from the outside in as a sociological enterprise, not a purely intellectual one. Today I'm going to talk about a very important distinction that looms large in my view of mathematics, that between the exact and the approximate. But I feel that it doesn't get enough play in the rest of the mathematical community of pure mathematicians. So we're going to talk about this distinction today, and I'm going to try to convince you about why it is actually so important. Let's start off with two quotes, one from Henri Poincaré, a preeminent French mathematician, the late 19th, early 20th century. He said, "Approximate is the enemy of exact." They're on opposite sides of something. Our second quote from Carl Friedrich Gauss, the great German mathematician. "Exact science is the knowledge of exact values. Approximate science is the knowledge of approximate values. The distinction between them is the distinction between exact and approximate knowledge." As a first approximation, it's useful to associate applied mathematics with approximate values. Scientists, engineers, people who are working in the real world, they don't often need exact values for measurements. Approximate values are perfectly reasonable as long as they have a certain required precision. We associate exact values and exact notions rather more with pure mathematics. That's a simple but important distinction. So as an example, let's look at arithmetic. So exact arithmetic involves, say, natural numbers and integers and fractions, otherwise known as rational numbers. In these domains, we can do arithmetic exactly. So 6 times 7 is exactly 42, etc. And that's really a kind of a pure mathematics realm. The corresponding approximate numerical system, which is actually more oriented towards applied mathematics, is the decimal number system, or scientific notation, where we work with decimal numbers to a certain precision, represented by a certain number of decimal places to the right of the decimal place. And good examples of those are historically log tables and trig tables, which are necessarily somewhat approximate, but they're still very useful. And the sort of more accurate they are, generally the more useful they are. But it's well understood by everyone that these are not exact things, they are approximate things, and therefore they are perfectly useful for applied mathematics. As an example of the distinction, so here's a number, 35,417,598. A pure mathematician might be interested in that number. An applied mathematician is probably not going to be interested in that number, or a scientist or an engineer. If an engineer or a scientist is counting something and this is the exact number, that's probably not of interest. It's probably more useful to say, oh, it's about 35 million, or maybe it's 35,400,000 roughly. So that's represented by the scientific notation. That expresses it in an agreed number of significant digits and then a power of 10. So this is an approximation, but it's somehow more succinct and concise and drops off extraneous, unnecessary precision. Here is an exact fraction coming from rational mathematics, say 1613 over 72,048. As a decimal, this is approximately 0.02238. And as the Flemish mathematician Simon Steven advocated in the probably the 17th century, maybe it was even 16th century, there's a lot of benefit to working with this kind of framework rather than with fractions, because it's hard to assess accurately how big such a fraction is. This is much more useful for everyday work. Okay, so even at the elementary, high school, or even primary school level, this distinction between exact and approximate in arithmetic is well known and is a major feature of the mathematical landscape. So in the latter half of the 19th century, pure mathematicians, motivated by former difficulties in analysis, calculus, eventually started realizing that they needed to tighten up their understanding of the underlying numerical system representing the continuum, and this idea of formal arithmetic of real numbers was introduced. And it's at this point that I think that we went astray. So to me, this is like a major departure from logical correctness and really being based on the ground. So the real number story is an attempt to try to make certain things happen that we might want to have happen, sort of from a naive point of view. And it's best perhaps illustrated with the familiar problem of solving equations. In this case, just polynomial equations. So here are two examples where we have a degree 5 polynomial represented by this graph. In this case, x to the 5 minus 4x cubed minus x squared plus 4 equals 0. And in this case, almost the same, x to the 5 minus 4x cubed minus x squared plus 3 equals 0. So the only difference between being the 4 and the 3. The graphs are identical, but if you look actually not even too closely, you can see that there's a difference. Okay, this one goes up a little bit more there. These ones here actually go right through 1, 2, and minus 2 because of the fact that this particular polynomial factors. It factors as x minus 1 times x minus 2 times x plus 2, and then this quadratic factor x squared plus x plus 1. That has the consequence that if we're looking for solutions to this equation, in other words, zeros of this function, then they just correspond to these linear factors. So we get a solution x equals 1, x equals 2, and x equals minus 2 from these three linear factors. And you can see that graphically on the graph, x equals minus 2, x equals 1, x equals 2 are the places where the graph is crossing the x-axis. In other words, when the height is indeed 0. So this is a particularly easy kind of thing to solve because of the pleasant algebraic fact that this particular polynomial that I've chosen happens to factor in this very pleasant way. This is an exact situation. Over here, just with this small alteration, we move actually into an entirely different realm. So the reality is that these two situations are dramatically different, even though the modern pure mathematician does not really regard them as such. Okay? If I ask my computer to solve for x here, my computer will give me some answers, but they are in the form of decimals. That's representing the fact that this alteration in this last digit has moved the graph a little bit, and it's no longer exactly going through minus 2, 1, and 2 on the x-axis. Rather, the value here is roughly 2.03346, etc., some decimal. And here, 0.88340, ... and over here, minus 1.970906462, ... And crucially, these patterns are not rational numbers, so there's no repetition that occurs. So there's it's highly problematic to try to get one's hands on the exact x that's being represented here by these first digits. Okay? In fact, you can create an algorithm. So Newton famously gave an algorithm for generating better and better approximations to the zeros of a function like this in terms of an initial guess, and then looking at a tangent, and then giving you another second better guess, and then another tangent, etc. So Newton gave this prescription for moving closer and closer and closer to a prospective zero, but with the acknowledgement that this process is not necessarily, in fact, typically does not end. It's an ongoing process that just keeps you moving closer and closer to a possible zero. And that's what's represented here in this decimal. Okay, so actually these decimals go on forever in principle. Okay, and for me, what that really means is that these zeros, in an exact sense, don't actually exist. They're not real objects. The real objects are the approximations that we can obtain by running Newton's algorithm or some other version of that up to a certain point, and then taking the result and saying, oh, here we have an approximate zero. So if I lop off the three dots here, okay, then I've got three numbers which are approximate zeros, in the sense that you plug them into here. You're not going to get exactly zero, but you can get something that's pretty close. Okay, so this is really happening in the world of approximate mathematics, in the world of applied mathematics. And in fact, for practical solutions, this is all that an applied mathematician needs. Typically, a lot fewer decimal places are going to suffice for most practical problems. But I want you to be aware of this huge distinction between these two cases. Okay, they are not the same at all. Okay. And the pleasant exactness that we get from this very special situation is not reflected in the more typical situation. This is the more typical thing that you expect if you just write down some random polynomial and ask for its zeros. Now, that's not to say that there are not other ways of trying to solve this. Okay, so there are other ways. For example, algebraists have an approach to finding solutions that involves matrices, that involves sort of going up in algebraic sophistication. And in fact, in my Wild Egg Maths channel, have a whole series of videos that shows you how to get solutions to general polynomial equations using power series, okay, a different approach, which also has an algebraic aspect and involves the Catalan story augmented in a very beautiful way, I think in a quite interesting fashion. But so there are some alternatives, but the reality is that if we're sticking with the number line and asking for actually numerical values to solve such an equation, we have to be prepared to say this is an approximate problem which only has approximate solutions. That's just the way the mathematical world is. Currently, the Academy of Pure Mathematics does not want to recognize this distinction very clearly and prefers to suppress it. So with respect to the last example, this distinction is suppressed, and there's a so-called theorem called the fundamental theorem of algebra, which sort of insists that all of these polynomials should be treated sort of on the same footing, that they all have solutions if they have a certain shape. So the fundamental theorem of algebra would not distinguish between those two cases that I showed you. Okay? And it's the theoretical belief of the majority of my pure mathematician colleagues that in fact there is no theoretical difference between the two of them, while actually, visibly, computationally, practically, there is a huge difference. This distinction also happens in a lot of other areas. Okay, so I want to touch upon some other areas. And a good one is that of topological spaces, which in my view is hugely problematic the way it's currently presented. And I want to explain to you why. It's again this distinction between exact and approximate. So the world of topological spaces sort of intrinsically can be divided into finite topological spaces and infinite ones. Now, for curious reasons, the finite topological spaces have hardly seen very much development. So the vast majority of effort has gone into the infinite topological spaces side of things. But nevertheless, there have been some people who have worked in topological spaces of a finite type, and here's an example where we can sort of see everything laid out. So what is a topological space? Well, it's first of all a set. In this case, X is a set with 4 elements, A, B, C, and D. And then we require that we have a family or a collection of subsets of X called open sets. And these open sets should have two crucial properties: that the union of any bunch of open sets is itself an open set, and that the intersection of any bunch of open sets, actually in this case, perhaps should say any finite collection of open sets is also an open set. That restriction is not relevant for the finite case, but it's relevant for the infinite case. So here are a bunch of subsets of X. The empty set, just C, just D, C and D together, B and D together, B, C, D together, and the whole thing. And these 7 subsets have the property that if you take the union of any two or more of them, you get another one. So for example, if you take the union of this one and this one, you get CD, which is over here. And also the intersection of any two of them is in there. So if you take the intersection, say, of this one and this one, well, you get that one. The intersection of this one and this one is that one, etc. Now, the whole thing can be sort of visualized this way. You have 4 points, A, B, C, D, and these open sets are represented by these collections. So BD, for example, is represented by this loop here. Okay, the empty set is nothing in it. Okay, so this is an example of a topological space of a finite kind, and it's very explicit. You can lay it all out. You can check all the conditions, and it actually has interesting connections with combinatorics and other things. And a good reference is a book by J. Barmak called Algebraic Topology of Finite Topological Spaces and Applications. So in my view, this is exact mathematics because we're able to specify everything. We lay it all out in front of us. We can check the conditions of the definition involved and check that everything is working. Now let's go the big step to infinite topological spaces, where, in my view, things get hugely problematic. Although, again, this is finessed, but your average pure mathematician is not going to see this. They're not going to want to hear this, but it's nevertheless the case. So here's a particularly simple version, okay? There's more complicated versions too, so let's just stick with a simple version. So here's a topological space. First of all, we start with a set. In this case, it has to be an infinite set. That's what we're looking at. Say X is A1, A2, A3, A4, etc., and it keeps on going, 1 for every natural number. Okay, so that's the set. Now what we need is a bunch of open sets. What's an open set? An open set is a subset of this. So that subset could have a finite number of elements, could have 0 elements, like the empty set is always a subset. But there also could be finite subsets. But typically, in this story, the open sets are themselves infinite sets. So we have to look at infinite subsets of the original X. For example, maybe here's one. We pick A5, we pick A9, and we pick A3001, and then there's more, which I just left off. But you should think of, there's a whole list of further A's that are taken from X to make this particular open set. And then we have another one, say this one here, A2701, A this thing here, and furthermore, and again, this is an infinite set, supposedly, that carries on to the boundary of the universe and beyond. Here, this one here, well, it's actually more typical. The first one has an index. This is a natural number, so that's one of these guys. But it's a huge natural number that goes itself on for some time. It looks like it goes on at least 2 miles. Hold on, no, it's at least 200 miles. Oh, telescope. No, actually it goes all the way to Jupiter. Hubble telescope. No, actually it goes all the way to Andromeda. Just this index here, the first one on in our set. Well, so what kind of conditions do these open sets have to satisfy? Well, the intersection of any two of them is also an open set. So if I take this set and I take this set and I go through it infinitely, both of them, take the intersection, it's an infinite job, I get another presumably infinite set. That's going to be another one somewhere on this infinite list. And unions, not just 2, but in fact, if I take 4 or 5 or even an infinite number of open sets and take the union of them, then that should also be an open set. So there's a lot of checking to do. If you actually had such a thing, in what sense, I don't know, but if you actually had such a thing, there would be infinite amounts of work to make such a topological space. So this setup here that I've shown you, okay, is really essentially the foundational intellectual archetype, believe it or not, for our understanding of continuous spaces in the mathematical world. It's a little short of incredible because it's sort of obvious that this kind of thing is completely inaccessible. Now, if you actually take a course in topology, they're never actually going to get to brass tacks like this, because then it's obvious that you can't specify such a thing. But what they're going to do is they're going to have toy examples, okay, that are sort of cherry-picked so that you can make it look like you've got such a setup. So in some sense, you're sort of painting it from a distance and saying, well, we sort of have these things. We consider the set of all open balls, you know, in Rn or something, and then we take arbitrary unions of open balls, and those are our open sets. Okay, but you can't actually demonstrate them. So this entire story, in my view, is an approximate story. It's not exact mathematics because simply we're not able to specify exactly and precisely the objects that we're ostensibly talking about. And we're not able to verify completely and exactly the various requirements that this object is supposed to have according to the definition. Exact topological spaces, in my view, approximate topological spaces, which in my view is really intrinsically necessarily part of applied mathematics. Okay, let's talk about functions, which are workhorses of modern, say, 20th century mathematics. So, what is a function? Well, there's various definitions. It's clearest, perhaps, if we start with a finite example where we can lay things out exactly. So, we have a function from one space to another. In this case, the set X, consisting of the elements A, B, C, to the set Y, consisting of the elements 1, 2, 3. And here's the notation that we use. F is a function from X to Y. What does that mean? It means essentially that we have a table listing X values, and we should have every single element of X on the left-hand side. And on the right-hand side, we have the corresponding F of X's, which are elements of Y. So in this case, F of A is 3, F of B is 2, and F of C is 3. So it's not necessary that every value in Y is taken on, and it's certainly possible that some values here are taken on more than once. And we can visualize such a thing with a little diagram like this. Here's X with its 3 elements A, B, C. Here's Y with its elements 1, 2, 3. And these arrows representing the action of F. But crucially, in this case, the function, which is represented by this table, together with, first of all, this data of what the domain and the codomain are, and then this table of actual values, that specifies the function. Okay, now we go to corresponding infinite object. And this notion pervades modern mathematics. Everywhere you go, there are infinite functions, supposedly. And their definition is something parallel to this. Okay, and it has what shape? Well, in the general case, or at least a somewhat simple infinite version, we have two sets, say X and Y, and let's say that they're both infinite sets. X1, X2, X3, etc., Y1, Y2, Y3, etc. So these are what's called countably infinite. So these are the simplest kind of infinity, if you believe these mystical things. Indexed by natural numbers, both of them. So what should a function f from X to Y look like? What data do we need to specify a function? Well, the official definition really is essentially this, that you need a table, okay, or if you like, a set of ordered pairs, but it amounts to the same thing. You need a table where on the left-hand side you have every value of X, every element of X appearing exactly once. And on the right-hand side, the corresponding values in Y, the f of X values. So X1 gets sent to Y sub 5173. X2 gets sent to Y sub 61. X3 gets sent to Y sub this thing. X sub 4 gets sent to Y sub this thing. Oh, actually this one here, it's a natural number, but it looks like it's also going off to Jupiter and beyond. That's what happens when you work with natural numbers, right? Natural numbers get big. In fact, your typical natural number is huge. In fact, maybe this one even goes to the end of the universe, because there are lots of natural numbers bigger than the size of the universe. They don't fit inside the universe. Okay, so they're going to have to be on our list too. So I guess this thing here has to has to have a label which actually goes beyond our universe. We need some extra universes for this thing to run into so we can write it all down. Oh, sure. We have big imaginations. So this is the usual story. Actually, it's a very modest example. The general thing is often much more convoluted. But this is a simple example of a function in an infinite setting. And it's no exaggeration to say that this is a workhorse of 20th century mathematics. But I'm hopeful that in 21st century mathematics we'll eventually get a grip on these things and let go of this notion, okay? And try to replace it with more exact notions, because there's obviously an approximate aspect of this, because we're not able to finish writing the thing down, right? You can't write them all down. You can't write them, even these labels, all down. And so, of course, when undergraduates learn these things, they're not given this general kind of thing, even though this is actually representative of the definition. Rather, they're given these little toy examples that make them feel like, happy little consumers. Oh, let's consider the function y equals x squared plus 1 from the real numbers to the real numbers. Okay, you're supposed to imagine that. It's still a pair. An infinite number of pairs of real numbers, each one of them looking, vastly complicated. But the fact that you have a nice little formula for it sort of hides the complexity. But if you ask the analyst, well, why don't you just stick with the formulas? Why don't we define functions in terms of formulas? They'll quickly say, well, that's not general enough. That does not meet our requirements. Those are just toy examples, so to speak, to make undergraduates happy, to make them feel as if they're doing something that's actually meaningful and computationally reasonably valid. The general case, far beyond even those with extreme imaginations. So let's have a look at this function concept in the domain of number theory, which after all sounds like it's quite down to earth, talking mostly about natural numbers and their properties. So on the exact side of things, I want to look at a function, which is actually a very important number theoretical function. So we have a natural number, say n. Then sigma of n is the sum of the divisors of n. So sigma of 1 is 1 because 1 only has one divisor, which is 1. Sigma of 2 is 3 because the divisors of 2 are 1 and 2. Sigma of 3 is 4 because the divisors of 3 are 1 and 3, sum to 4. Sigma of 4 is 7 because 1 plus 2 plus 4 is 7. Sigma of 5 is 6 because 1 plus 5 is 6. And sigma of 6, which is quite interesting, is 12 because that's 1 plus 2 plus 3 plus 6. It's 12. That happens to be actually twice 6. It's a very special case, that case of perfect numbers. Okay, so that's a rather cut and dried function. And in this case, even though we're going from an infinite set to an infinite set, we are able to specify this in a way that's different from what I told you before. We do not need actually an infinite collection of ordered pairs because the actual formula itself is sufficient. So we can alter our point of view and say, okay, we're going to stick with the formula as the actual meaning of this function. Okay. So here on the other side, on what's really the approximate side, okay, is a very famous function called the zeta function, the Riemann zeta function. And it's also inputting a natural number n and outputting a so-called real number, that is like an infinite decimal. Okay, and the definition is that we're taking the infinite sum, k equals 1 to infinity, of 1 over k to the n. What does that mean? Well, so n is fixed, n is like a natural number, like 7, okay? And then we're taking the sum 1 over 1 to the n, plus 1 over 2 to the n, plus 1 over 3 to the n, plus, 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 and we're adding up these infinite number of things. So, for example, if n is 7, we're adding up 1 over 1 to the 7, plus 1 over 2 to the 7, plus 1 over 3 to the 7, plus so on. Now, for me, this doesn't make sense, for the simple reason that this is not part of our arithmetic. When you're defining arithmetic with rational numbers, you're not in a position to define the sum of an infinite number of rational numbers in general. Now, the modern analyst would like to think otherwise would like to think, well, no, we can take the limit in some suitable sense. There's some object at the end of the road after we've gone infinitely far, and that object is the real number, which is the sum of these things. And we can get an approximation to the final sum, by just sort of truncating this sum and evaluating it. So in this case, my computer tells me this is 1.008349277389192, and it goes on in some fashion that I have no idea about. Although I could get my computer to spit out a few more hundred digits if I wanted to. But really, is this really a coherent theory? I say it's not. Because what we're really doing here is we're looking at something which is essentially approximate. You see, this sum here really represents like a computer program that's churning away. Okay? It's subsequently adding one more of these reciprocal numbers to the current sum. So we have some big rational number at some point, and then we have to add another reciprocal power, and then we get a bigger rational number, and then we have to keep doing it. We just keep doing this, and the rational numbers that we get are bigger and bigger in the sense that the denominators and numerators get bigger and bigger. And from my point of view, that's all that ever happens. Right? You're never at the end. You never get to the end. You're never in a position to say, okay, now we're finished. Now it's over. Now we have the thing. So from my point of view, it's crucially and fundamentally wrong to refer to an it, which is the result of this infinite computation. So the statement that this is an approximation to it, where it is this infinite sum, is in my view wrong, because the it itself is not something that's obtainable in our universe. There's too much complexity involved here. This thing blows up long before you get to infinity. Okay, it blows up. The entire universe is insufficient to house this thing. Okay, so there's no sense in which this thing exists in our universe. Now, the analyst might say, yeah, but in some alternate universe, we can kind of imagine that this thing exists. For example, if a slimy intergalactic super octopus is perhaps listening to this video, hello, slimy intergalactic super octopus, from another universe, a universe where there's an infinite amount of room, and where the super octopus has an infinite brain, an infinite number of arms, infinite amount of room, its hard drives are infinite. Well, in such a universe, I will admit, you slimy intergalactic super octopus, you are likely to be able to make this computation and write it all out and say, here's the result of the computation. So this objection does not apply to you. Okay, it only applies to us meager mortals here in this particular universe, with these particular laws of physics and the reality that's actually here and now. In this world, we're not able to finish this computation, so it doesn't even make sense for us to talk about the result of completing this calculation. Here's another way of thinking about it. Imagine an infinite ladder. Okay, whatever that means, okay? You have rungs, rung 1, rung 2, rung 3, you can climb up the ladder. 4, 5, 20, 3,000, 4,000, a billion of 1, a billion. So you're climbing up this ladder. It just keeps on going up. Now, suppose I say to you, okay, you hang on a second. Why don't you just go to the top? Just go to the top. You look up. There is no top. There's just rung after rung after rung that's keeping on going. But I'm telling you to go to the top. So I can just, after this line, say, and now we go to the top. We go to the top of this infinite ladder. Okay, what does that mean? The only real sense of this is in terms of an approximate mathematics. I mean, if you actually want to be logically clear, okay, what we're doing is we're just talking about approximations that are obtained by running our computer programs, say represented by this thing here, to a certain level, and then having an output, and then talking about that output. So this is not a real function, it's an approximate function. It's a function in the world of applied mathematics. So to clarify this important discussion, let's have a look at a finite sum for this zeta of 7. So just the sum from k equals 1 to 10 of 1 over k to the 7. So my computer will quickly calculate that. That's this rational number here, starting with 650, and then all these numbers here. So it's quite a lot bigger than trillions, okay, and also a suitably big denominator. And remember, numerically, this is like 1.08 or something, 0.008. So it's a little bit bigger than 1. So this is the kind of thing that you can expect. This is only up to 10. Okay, we've only gone 10 steps in this infinite journey that we're proposing to take. So you can quickly see why this is, it's logically insurmountable, that this is not possible to do. You're not able to do this because this thing just gets so huge. Long before you get to infinity, okay, long before you get to infinity, all you have to do is go up to, probably, 10 to the 10 to the 10 to the 10, just a small tower of 4 tens. And you're already way over the size limit of the universe. Sorry, your computation has to stop. You've run out of room. You've run out of memory. You've run out of energy, time, patience. There's physical bounds on what we can do. Now, there's a sort of a philosophical brand of mathematicians that says, well, we don't care. We can just think whatever we want. And that's true, you can think whatever you want. But if you want to think thoughts that actually have some connection with the world in which we live in, okay, then your thoughts should be in accordance with the real aspects of the world in which we live in. So positing that you can make computations that you can't actually do, I think is contravening the laws of logical honesty. Now this, of course, has very interesting implications for the most famous unsolved problem in mathematics, the so-called Riemann hypothesis. Now the usual Riemann hypothesis, as a consequence of this kind of thinking, we see it's really a kind of a dream. Or if we prefer, we could say that's really part of applied mathematics, because the usual Riemann hypothesis is all concerned with this zeta function and its various analytic properties as a function on the complex plane. But what I'm trying to tell you is that the reality is that it's not a real function, for the simple reason that you can't compute its values. And if you're a number theorist, I know you're going to kick and scream, you don't want to hear this, but just gather your thoughts and tell us, what is zeta of 5/4 plus 1/3 I? Okay, real part bigger than 1, this thing should, elementary, you don't even have to do much analytic continuation, so you can just compute it. And what do you actually get? Actually. Exactly. That's the crucial word. What do you exactly get? And you're not going to be able to tell us. What you are going to be able to tell us, well, you approximately get such and such. And what you're getting is an approximation to it. But I'm saying the it is not in existence because the it is not properly defined. Because the it itself requires this assumption that you're able to do a certain amount of work that you're not actually able to do. Okay. So the very basic object that the Riemann hypothesis is concerned with is not a legitimate exact mathematical object in pure mathematics, even though it certainly has an approximate nature. Now, what about the Riemann hypothesis, though? Well, there is still hope, because it turns out, very interestingly, that this is such a famous conundrum, that people have looked at it from all kinds of different directions. And in particular, people have looked and found very interesting alternatives to the usual formulation. The usual formulation is in terms of some analytic function that you get by taking the formula that I gave you for natural numbers, extending it to real numbers, then extending to the upper half plane, then doing analytic continuation to the entire plane to get a function who supposedly has non-trivial zeros along the critical strip where the real part is a half. Okay, that's the usual formulation. But there are quite a few alternate formulations that curiously don't seem to have anything to do with that complex analysis formulation. And in particular, there are fascinating reformulations that can be expressed purely in terms of natural numbers. Now that's very promising, because that means that there's at least a hope of extracting something that's actually logically viable, that we are able to frame the conjecture at least in a logically viable fashion, purely in terms of natural number arithmetic. And a good place to have a look at that is a book by K. Brouwer called Equivalences of the Riemann Hypothesis, actually 2 volumes, Volume 1 and Volume 2. And at some point I'm going to have to talk a little bit more about some of these interesting alternatives. Okay, so I've given you a taste, I hope, okay, of the important distinction between exact mathematics and approximate mathematics. This distinction is crucial for me. It colors all my view of mathematics. And I'm hoping that perhaps you too can benefit by being a little bit more aware of this distinction. You see something, you ask, wait a minute, is this an exact thing or is it an approximate thing? Correspondingly, are we really working in pure mathematics here, or are we working in an applied kind of setting? There's nothing wrong with working in an applied setting, of course. Applied mathematicians do great things. But we have to recognize where we actually are from a logical point of view. Okay, so now there's lots of other areas of mathematics that I could also have a look at in this context. For example, differential geometry or functional analysis or algebraic geometry, algebraic topology. And I will probably want to do something like that in another video. So I really want to convince you that this division really cuts across probably so much of modern mathematics. I'm Norman Wildberger. Thanks for listening.